Okay, Math 170. We are looking at 3.9 today. Antiderivatives is going to get us in the mood for chapter 4. So let's look at the first idea of what is an antiderivative. So I'll define it. A function f is called an antiderivative of a function with a lowercase f on the interval I if capital F prime x equals f of x for all x in I. So we're kind of looking at what was the function before we took the derivative. So if I can throw in an example, sometimes that helps a little bit. Let's see, we have, let's try this. F of x, our capital F of x, is 1/3 x cubed. That's an antiderivative of the function f of x equals x squared. And so what I'm looking for, if I'm kind of thinking about what I mean by antiderivative, I want to look at the derivative of what is x squared. So if we're going to play with this, we can kind of check it just to see. If I were to take the derivative of capital F, that would be 3 times 1/3 x squared. The 3 times 1/3 cancels out to be x squared. So that is, in fact, our antiderivative. Now, another note for you, just in case, you could have chosen many antiderivatives. We could have chosen capital F of x equals 1/3 x cubed plus 2. Anything actually adding or subtracting a constant would also have worked. 1/3 x cubed, let's say minus 7. Notice if you take the derivative of those capital F of x's, you will get x squared back. So we're going to kind of train you to think, and then I'll try to give you a pattern to see what always works when we have powers. So let's start off with some of the rules we already know. If we're trying, again, we're looking for antiderivatives. So we're actually looking at the opposite of what we've been doing the last 2 chapters. We're going to look at f of x equals 5. So if I'm thinking about this, I'm going to say the derivative of what is a constant. So sometimes if you want to just get your brain moving a little bit, I might think of like maybe starting off, for instance. I might say, well, I know that the derivative of a linear term should be a constant. So a lot of times what we'll do is we'll set our capital F of x equal to a constant times x. So then that kind of helps us out with understanding, okay, if we took the derivative of capital X, we would get an x, excuse me, gotta be careful, k is the constant, not x. So we would get a k. And what you can do to help you out with this is you can set it equal to the 5 that we already see in our constant right here. And that kind of tells you what we want. It already tells us, all right, well, that means k is going to equal 5. So when we come up with our f of x, all we have to do is plug it back in. So therefore, f of x equals 5x. And you have your antiderivative. So what you want to look at, you kind of have to look at the patterns you've been playing with already with taking the derivative of everything. So if you have a constant times x, the derivative is always the coefficient. So we can think backwards and say, okay, 5x must have been the antiderivative. And we'll have a better way to look at it, but I just want to get you thinking a little bit more before we introduce that. So similarly, now we have the f of x equals 5x. And again, we're looking for the antiderivative. So a lot of times, sometimes I'll just take the constant out of the mix just so I can see this a little bit better. So if I can look at just x, the first thing we're trying to do when we're trying to answer the question is ask ourselves the derivative of what is 5x, but you may want to go even a little bit more precise and ask yourself the derivative of what is x. So you can kind of play with it a little bit and think, well, if we're trying to find something, a function, maybe we just got to pop up a power. So maybe if I can kind of play with x squared a little bit, I know I'll have a constant involved. So for instance, if I take the derivative of x squared, that's 2x. So I know that there's going to be a 2 involved. So what I want to play with is the starting point one more time. And say, okay, let's start off with trying to understand what our constant would be. And so I'll start off with a constant times x squared, because I know if I take the derivative of it, I will have the k that I can pull out. But if I take the derivative of x squared, it would be 2x. And now I'm going to set it equal to what I want. I want to set it equal to the f of x, or lowercase f of x. And this allows us to solve for who k is. So you can kind of notice if we're solving for the k, the x's will divide out. And so we get k times 2, or 2k, equals 5. And if you solve for k, we get k equals 5/2. So then what we can do for ourselves is say, well, therefore, now we're going to know what our function is. Capital F of x is equal to k, which is 5/2, times x squared. And if you're not sure if you chose the right function, you can always see if you want to take the derivative just to check it. I would not circle this part, but you can say, what is the derivative of capital F of x? And you can say, okay, that's 2 times 5/2 times x. And then once we, yes, that's true, Leica. It is. 2 times 5/2 canceled out with the 2's, and we end up getting a 5x. So it kind of helps us verify, like, okay, we chose the right antiderivative. Now, keep in mind when we were playing with the antiderivatives, we could have added constants to any of these antiderivatives and we'll still get our result back. So we'll account for that a little bit later. Key word being, they asked us to find an antiderivative, not all of them. So let's play a little bit more before we introduce some shortcuts. I want to find an antiderivative for f of x equals x cubed. And so this is what I have to think backwards. I have to think the derivative of what equals x cubed. And so by now, all the experience we've had taking derivatives of powers, we know that every time you take a derivative of a power function, it drops the derivative or the exponent down by 1. So I know my starting point would have to be something that involves an x to the power of 4. So this is where I have my constant multiplied by x to the 4th. So now you can kind of check, okay, if we take the derivative of capital F of x, this will leave us with 4 times k times x cubed. And now what we're going to do is we're going to set it equal to what we want it to be, which is in fact, it's just x cubed according to our starting function. And you could kind of see how the x cubes divide out. So we end up getting is 4k equals 1. And so if you solve for k, you get k equals 1/4. And so that'll help us out a little bit. Therefore, if you really want to name the antiderivative, we're replacing k with the constant we just found. It should be 1/4 x to the 4th. And again, if you prefer to check just in case, feel free to. We do the same thing. And so the power functions involve a little bit of thought process. We want to also pull in some trig functions for you. If I'm going to look at f of x equals cosine x and I want to find the antiderivative, I have to think about the derivative of what is cosine x. And so sometimes it helps me to write it out in English just in case. So I think, well, I remember if I took the derivative of sine, then I would get a cosine x back. Now, we didn't have any extra constants on this, and there's no extra complications in the argument. So right away, we can name who their antiderivative is. Capital F of x would be sine x. So sometimes the trig functions, if you have a good idea of what the derivatives are, can be helpful. Or if you prefer, sometimes if you start off by writing a list of your functions just to begin with. For instance, if you start off with f of x equals sine x, cosine x, tangent x, and so on. You can then talk about what the derivative is. So derivative of sine x is cosine x, derivative of cosine x negative sine x, derivative of tangent is secant square x. Now you could kind of go backwards and say, well, what we're really looking at is the antiderivative. So if we go backwards, we're just saying, what was it before we took the derivative? And by the way, feel free, we can keep continuing on. Don't we have also cosecant x, secant x, and cotangent x? And so if you remember, derivative of secant x, I kind of go with tangent for now. We have secant x, tangent x. And so that kind of helps me with derivative of cosecant x. It's the opposite. So we have negative cosecant x, cotangent x. And so derivative of cotangent x, negative cosecant square x. Oops, let's write this down. So now sometimes if you have a chart when you're first starting off, if you know the derivative, you can think backwards to find your actual antiderivative. Okay, so now that we've kind of thought a little bit about the power functions, I want to kind of give you a formula to help you out. Sometimes you don't have to go through all of this finding the constant if you know the pattern. So the key is understanding anytime you have a power function, that's x taken to an well, doesn't even have to be an integer, x taken to a real number, as long as that real number is not equal to -1. The nice pattern tells you that the antiderivative is x. You probably already guessed it. You're always going to add 1 to the power, but you have to remember to divide by the same expression. So if we want to look at what we had earlier, just in case, and I'll go through example 2 in a second, but just looking at maybe, what was that, example 1b. And we wanted to say, what's the antiderivative? What was it? F of x equals 5x. Well, if you want to find the antiderivative, again, the constant's not going to have an issue. What do we want to do is take our x. It already had a power of 1. So according to our formula, we're going to add 1. And then what happens is we take all of that and we divide by whatever this exponent is. So it's 1 plus 1. And I know you can do this in your mind, but sometimes when we get a little bit more complicated, it's nice to write out our thoughts. So do we have 5x squared over 2? We kind of look at our answer, and that's what we had found earlier. So nice little shortcut to help us out. So now we can kind of adjust a little bit and say, okay, well, if we have f of x equals square root of x, sometimes it's a little bit nicer to start off by rewriting it, just so that we have a good idea of what to look at. Radicals can be written as fraction exponents, rational exponents. So now if we're going to use our formula, we can say the antiderivative is equal to, we're going to keep our x. What we're going to do is we're going to add 1 to our exponent, and then we will divide by the same exponent. So keep in mind, remember, it's not just the 1 you're dividing by, it's whatever the result is when you add 1 to the exponent. And especially if you have fraction exponents, I prefer to show this workout just so I don't get messed up on any of the math. So x to the 1/2 plus 1, 1/2 plus 1 is 3/2. So that means in both cases we have 3/2. And then we know if we divide by a fraction, it's the same as multiplying by a reciprocal. So what we end up getting is 2/3 x to the 3/2 as our antiderivative. And that's good enough. If you want to rewrite it back as a radical, that's fine, but for purposes of our class, we don't necessarily have to. Maybe if we're plugging in numbers later. So I think you're ready to kind of play around with a little bit more complicated examples. So we're going to look at example 3. And part A is finding that we need to find the antiderivative or an antiderivative. So be careful. The difference between the beginning of the chapter and chapter 2. So if we're finding an antiderivative, we have to figure out what the function was before you took the derivative. So again, you're going to ask yourself, okay, the derivative of what is cosine 2x? And because the argument is a little more complicated than just an x, we want to use what we're looking at as one of our techniques from earlier, where we kind of think about what's our starting function. So I kind of have an idea. The derivative of question mark. Question mark should have to involve a sine x, but it should involve the sine of 2x. But there could be a constant happening. So I have to kind of attach this in terms of understanding what k is. So we should have k times sine of 2x will give us what our antiderivative should be. Now if we take the derivative, of k times sine of 2x. Now constant is k, derivative of sine is cosine of 2x, but we also have to talk about the chain. So derivative of the inside is 2. If you prefer to clean it up, that's fine. That's 2k cosine 2x. And now what we would like to do for ourselves is we're going to set it equal to what we want. And what we wanted was the negative 1/3 cosine of 2x. And if I want to, just to make sure, I'm closing the argument in parentheses. And we kind of do this idea is that if we do have two expressions being set equal to each other, you don't necessarily have to think about it as you're dividing out, because sometimes these guys are 0. But you can say if two expressions are equal, then we can set their coefficients equal. So we get 2k equals negative 1/3. And then if we solve for k, We have multiplied by 1/2 on both sides. So we should get k equals -1/6. So that will give me, if I'm now kind of going back to my original starting point, k gets replaced with -1/6, and we end up having sine of 2x as the rest of the antiderivative. So now we kind of think a little bit more about what happens if we have a combination of two different functions. So there's a couple things I want to play with. I kind of see that there's a radical, and that's going to be helpful for me because I can split it up. It could help me to understand that my f of x, at least part of it, is equal to 2 times x to the 1/2 power instead of writing it the radical form. And I can start off by saying, well, I know since I have a power function, I can find that portion. So the constant is going to remain the same. What do is I take the x to the 1/2, I add 1 to it, and I divide everything by the result of that exponent. So we can kind of just take it easy on this part and take your time. Still, that's 2x to the 3/2, still divided by 3/2. And now if you want to play with the math, 2 divided by 3/2 is 2 times 2/3 x to the 3/2. So that should give us 4/3 x to the 3/2 for that piece of the function. So we'll get back to that. Sometimes it's nice to just get things out of the way if you already have a formula for that. The next thing I want to do is approach the little rougher part. We have this secant square of 3x. And so a lot of times what you're doing is we can go back to our chart if we need to and say, okay, we see a secant square. What was the derivative that made a secant square? And so a derivative that makes a secant square is derivative of tangent. So that's going to help me out a little bit. So kind of my thoughts. My question involves tangent of 3x. We just don't know the constants quite nicely yet. So we can go with our starting part. So let's think about this. We're going to start off, and I'll combine the two functions later, but we're going to look at a few things. We can say f of x equals k times tangent of 3x. Here we go. Now when you take the derivative, the constant gets pulled out. Derivative of tangent is secant square 3x, but you still have to multiply by the derivative of the inside, which is the chain. So derivative of 3x is 3. If you'd like to clean this up, that's 3k secant square times 3x. Now, what you can do is you can set it equal to what you need. In our case, it was secant square 3x. And so we notice if we have two expressions that have the same trig function, that's going to imply that our coefficients are equal. So that's going to tell us that 3k is equal to, and by the way, you can't see this, but the coefficient of the secant square is 1. So what do we do is solve for k, and we get k equals 1/3. Now, if you want to piece this together, remember that the two functions were being subtracted. So we could look at it as the antiderivative of everyone. We started off with 4/3 x to the 3/2. And remember, we had a minus sign separating our two functions. And now, if we're looking at finding the rest of our function, we should have minus 1/3 tangent of 3x. And we have our antiderivative of a more complicated function. Now, alternatively, I kind of took these off into separate pieces. If this was something you are interested in, anytime you see a sum or difference, one alternative way, just so that we can kind of maybe piece it together, you could have started accounting for everyone. So what I would look at is my f of x was equal to, let me write this in a different color. It was originally equal to 2 root x minus secant squared 3x. And of course, if you preferred to rewrite it so that the radical had a rational exponent, that's completely fine. But just understanding what the starting point was. Now, if you wanted to talk about your antiderivative, you could have said, okay, well, we could just figure it out based on what we're looking at over here. We could play with the idea that we were dealing with anytime you take the derivative of x to the 1/2, we could have looked at the fact that, well, derivative of x to the 1/2, or derivative of, I shouldn't say derivative, I should say antiderivative. We should have something where it's 3/2 times k x to the 1/2. So it kind of gives us an idea of what we were looking for. And I should be a little bit more precise as to what I'm thinking about. So let's remind ourselves, what was I doing here? Remember, I'm finding the antiderivative of this power. I'm gonna not deal with the 2. I'm gonna say, what is it? X to the 1/2. We add 1 to the power. So let's make this a little nicer for you. I should have x to the 1/2 plus 1, which is 3/2. If you divide by 3/2, you get 2/3. So this is kind of where my pattern is coming in. But remember, I had to account for a constant because I'm not sure. So I've got a k. So I could kind of help with that a little bit. And what I'd like to do now is take my work from my, where is it? My secant square, excuse me. And do the same thing we're looking at over here. So we still have k times tangent of 3x. Okay, so I'm just double checking here. Here is the issue though. You end up having 2 k's in the problem. So what we end up doing is we want to make sure that they're not going to be the same value. We don't know if they're the same value. So this is what we end up calling them with subscripts. So I end up having let me write it down for you, excuse me. And before I start erasing everything, I should be careful. So I'm going to call the first one K1. And I remember I had a, was it a 3/2? I think. 3/2. X1, X2, I'm going to say, oh, wait, no, 2/3, excuse me. Okay, so then the next thing, I had a K attached to the tangent. So I'm going to call that K2. You could choose, you know, A and B, whatever works for you. I just use K's because I know A and B's are always used, but go for it. And so at this point, what we can do is you can then compare coefficients of your original function. So if I can kind of go back to my original function, which was f of x, and actually I'd rather look at this part here. Now, before we do everything, let's make sure. Did I skip? I skipped a step. I apologize. Let's try this a little bit better. Sometimes we have off days. Today's my off day. Let's do this. Okay. Let's go back to the start. Okay, so remember my idea was I was trying to figure out, I know I have to add 1 to the power. So 1/2 plus 1 is 3/2. And I know with the secant square, I know I have to have a constant. But I know derivative of secant square is tangent. So I know I have to have something multiplied by a tangent of 3x. Now, back to the whole idea with the case. I just called them 2 different numbers because I don't know that they are in fact the same. What I happen to forget is, we were trying to find the derivative so that we can actually compare this to our original function. So I'm going to take the derivative of everyone. Probably would be helpful to explain that to you. So we have 3/2 gets multiplied by k1. And then what happens is when you subtract off 1, if you're taking the derivative, you end up getting x to the 1/2. Same story if you want to take the derivative of the tangent to prove why we're trying to set things equal. Derivative of tangent is secant square. So I still have k2 secant square 3x. And now I'm going to multiply by the chain. And in this fact, this is where the 3 is coming into play. So now this seems to work out a little nicer. So at this point, just clean it up a little bit. I have 3/2 k1 x to the 1/2 minus 3k2 secant square of 3x. Okay. So now keep in mind what we're trying to compare things back to. We are trying to compare things back to our original function. So again, if we're looking at, and I'll do some erasing so we don't see all of the highlighting, if it will let me. There we go. If we look at our 2 terms, the term that had x to the 1/2 power, we then compare the coefficients. So we should have 3/2 k1 is going to equal to 2. And then look at the other one. If I'm looking at the secant square, I'm going to compare the coefficients of the secant square. So what I have at this point is 3k2 equals 1. Now, depending on what you want to do with the sign, sometimes I just keep it into play. Mainly, I already knew it was a negative, so might as well drop it down. If you preferred, you could also just start off with plus signs, and then it's evident after you do all the work. But now, when you end up solving for your k1s and your k2s, what do we have? 2, we're going to multiply by 2/3 on both sides. So we should get k1 equals 4/3, and then k2 equals negative 1/3. Kind of look at what we figured out already. I'm going to shrink it down so you see. It's the same. We verified. Yeah. 1/3 is the coefficient of x to the 3/2, and negative 1/3 is the coefficient of the tangent of 3x. So something to think about. I tend to like to split it up when I first start or when I'm warming up. And then we can go from there. We'll have a little bit better time, I suppose, when we start playing with some of these initial value problems. I'll give you an idea there. Okay. So Remember how we kept mentioning back over here that when you find an antiderivative, you're only finding one of them. There happen to be a lot more if you account for all the constants that you could run into. So remember, the issue comes when the derivative of a constant is 0. So this theorem should help us out a bit. And they're basically saying is if you find the general antiderivative or an antiderivative, if you add on any constant, then it's also an antiderivative. And you can add or subtract because, you know, subtraction is the same as adding the opposite. So they call C the constant of integration. And you're like, okay, C stands for constant. And this time they kind of made it capitalized because we're kind of trying to refer to antiderivative notation is usually used a capital F of X. So if we're playing with this, if you want to find everything, we always say that F of X plus C is the most general antiderivative of F because it accounts for every single antiderivative that could possibly happen. And I know that's impossible to list. So just to give you an idea what we're trying to get at, and really the moral of the story is we need to add C every single time. And you'll see we'll hit that up a lot in chapter 4. We're going to find 3 antiderivatives of f of x equals -5/7 secant 4x times tangent 4x. And then we're saying, oh, 3. You want 3 of them. So the first thing I'm kind of looking at is the fact that I see the trig function. And then my thoughts immediately go to derivative of what is going to give me a secant of 4x times tangent of 4x. And so that what part has to involve derivative of what is secant x tangent x. Well, it's the derivative of secant of x. And again, I always kind of prefer when we're first starting, and we're going to get a little more comfortable from now until calculus 2, write out your functions and the derivatives side by side so that you can directly understand and see the patterns when you come up with them. So we're going to start off again. Same idea. I'm going to start off with my thought is that my original or my antiderivative has to involve a constant times the secant of 4x. Now I'll take the derivative. So can pull the constant out. If I take the derivative of secant of 4x, I should get secant of 4x times tangent of 4x. But I have to remember I have to multiply by the derivative of the inside. So we're using the chain rule. So there's a times 4 at the end. We're going to clean this up a little bit. I'll put the 4 in front. So I have 4k secant 4x, tangent 4x. And now what I'm looking at is I'm saying, well, I see the secant 4x, the tangent 4x. So now I'm going to look at comparing the coefficients. So that's going to give me 4k equals -5/7. And solving for k, can multiply by 1/4 on both sides to make life easier. I should get k equals -5/28. So therefore, here's an issue. I've got the antiderivative or an antiderivative. I'm going to look at -5/28 times secant of 4x. Now that's one of them. They wanted 3. So you're going to just use the above theorem. And you're just going to add on a constant or subtract off a constant. So we can just say we also have another one. Keeping this -5/28 of secant of 4x. Add on anything you'd like. So let's add on 1. So that is your second antiderivative. And then another case you can do. Maybe you want to subtract off something. Any constant works. So who cares? Let's use pi. Why not? And so that's a third antiderivative. In fact, any constant, whatever works for you, it should work out. And then if you're kind of restating what we did earlier, a little note. If we were kind of applying the above theorem to our problem, the antiderivative f of x equals -5/28 secant of 4x plus c. That's the most general. Antiderivative. And it represents, I like the way they use this notation, it actually represents a family of antiderivatives. So that might be a little more friendlier. They all kind of look the same when you're dealing with x, but adding or subtracting on any constant will account for all of the antiderivatives. So nothing really new. Kind of the moral of the story is you basically take what we found earlier and we're adding on c. And that helps us determine that, okay, we can replace c by any constant and we'll find any of the antiderivatives to apply to our situation. So get really good at power functions, trying to convert them, figuring out what the derivative was beforehand, and also get really good at trig functions. We utilize those a lot, not just now, but Calc 2 uses a lot of the trig functions a lot more. The last thing I'd like to show you is an idea of initial value problem. And it kind of involves us finding one or more antiderivatives that are going to satisfy a given set of initial conditions. So for example, 5, they want us to find the original function f of x such that the derivative of that function is x times square root of x, and f of 1 is 2. And that's kind of where we're getting our initial value name. This is an initial condition. Mainly because it is referring back to your original function f. So sometimes they don't use this idea of antiderivative, but if they give you the derivative and they want you to find what the function was ahead of time, we could also refer to this guy as the antiderivative, if that's something you're interested in. After chapter 3, you really stop using this capital F notation. So I'm just going to kind of work it through, just kind of dealing with the idea of original function versus derivative of the original function. And that helps us with notation later. So keep in mind, when we're looking at this derivative, it's a product of two functions, x times square root of x. So we would have a hard time of finding an antiderivative if we have to completely deconstruct the product rule. So we always are looking for easier ways to approach problems. And one of the things that we kind of will stick out in our mind is that whenever you see a radical, like we said earlier, rewriting the radical using rational exponents may help us a little bit more with understanding what to do. So once I do this, rewriting this radical with rational exponents, and square root of x is very popular. You've probably noticed the last few examples. This kind of gives me a route to take, or I'm saying, wait a second, once I rewrite with rational exponents, I kind of have an idea that I'm actually multiplying with the same base. And when I multiply with the same base, what's actually happening is I don't have to write it as two separate products of x. It's actually x to the 1 plus 1/2, which is 3/2. So you're keeping the base and you're adding the exponents. And that just goes back down to, where was that up? The old exponent laws that you studied back in algebra. So that's where we're getting that. So we just took this and we wrote it into a nicer form. And this is more convenient to us because now what we have, now this is a power function. And we know once we have a power function, the whole idea of x to the n plus 1 over n plus 1 is going to be helpful. So this is going to allow us to find our antiderivative, or the original function. So this will give us f of x is going to be the same thing as x to the 3/2. And remember, with the power rule, what do? We add 1 and we divide by that same expression. But the main thing I want to point out is that we have to account for the constant c. So this is where they tell us, let's add the constant c right now. We're going to take care of all the antiderivatives at once. So let's clean this up. So x to the 3/2 by, plus 1. 3/2 plus 1 is 5/2. And if you're dividing by 5/2, you'll start to see some patterns. Dividing by 5/2 gives us f of x equals 2/5 x to the 5/2, and still we have plus c. So now we pretty much have our original function, but we have to find c. And how you find c is that they have to tell you some other information, i.e., the initial condition. So what I go through is I say, well, let's look at this one more time. Let's look at, I'm going to move it off to the side because I am running out of room. If f of x is equal to 2/5 x to the 5/2 plus c, my initial condition was f of 1 equals 2. So if f of 1 equals 2, you plug in 1 everywhere you see x. And so what that looks like, I have 2/5. Instead of x, I'm going to have a 1. So 2/5 times 1 to the 5/2 plus c, that is equal to, they gave us 2. Well, now you have an equation to solve. All you have to do is simplify and find what c is. And lucky for us, they only had us plug in the number 1, so 1 to the 5/2 means we still have a 1. So we end up having 2/5 plus c equals 2. Now what we want to do is just subtract 2/5 on both sides. So we should have c equals, if we were trying to combine over common denominator, I know we can use our TI, but what do we have? We need an LCD, so I have to multiply 2 over 1 times 5 over 5. So what does that give me? 10 over 5 minus 2 over 5, which gives us 8/5. So therefore, If you want to find your final function, final answer, my original function before I took the derivative was 2/5 x to the 5/2 plus the c, now we can replace with 8/5. And that is an initial value problem. It's pretty much you finding the antiderivative, accounting for the family of antiderivatives by attaching a plus c to whatever your result is, and then finding c using other conditions of the problem. And function notation comes back again. So one last problem, example 6 in this section. And we'll kind of see that it's a little more complicated, but still doable. Again, they want us to find the original function such that the second derivative is 12x squared plus 6x minus 4, given two initial conditions. So now we have, this is initial condition, there we go. And it's involving the function. And here's one more, it's initial condition, but this time it's involving not the second derivative, but the first derivative. Let me write that in a little nicer for you. So we'll still approach this the same way. When you think about what an antiderivative is, it's just what it was before you took the derivative. So if I want to kind of think through this problem, if I start off and I say, okay, what is the antiderivative of the second derivative? What we're trying to say is you just take one off. So it's the first derivative. And what we end up doing is we're saying, well, all of these end up being powers. So we can say, okay, we're looking at the constant. We have 12x. What do we do with the 2? You add on 1 and you divide everything by the same. Then we have the plus 6, still the same idea. You could add on 1. Divide by that result. And then with the minus 4, if you want to figure out what it was before you took the derivative and you got a constant, it had to have been linear. So that's where the extra x is coming from. And also remember that whenever you take an antiderivative, if you're accounting for everyone, you have to add a constant because we don't know what that was beforehand. So now I just want to clean it up a little bit. I should have 12x to the third over 3 plus 6x squared over 2 minus 4x plus c. And right away, kind of when you have very, very nice integer exponents, if you kind of see the pattern here, the fact that you started with an x squared, but now you have x cubed over 3, or you started with x to the first power, so now you have x squared over 2. That's kind of very useful when you're going through these a little bit faster. So one last thing, if I can reduce, I will. I should have 4x cubed plus 3x squared minus 4x plus c. And that, my friends, is what the first derivative is. But we still have to worry about the c. So what you want to do is you can look at and say, well, do I have any initial conditions dealing with the first derivative? And I do. So we're going to use our initial condition. We have to use the appropriate one. In our case, it was f prime of 0. So you take your first derivative every time you see an x. In this case, let's write everything correctly though. You should be able to plug in a 0 based on the function notation. And that was set equal to, in our case, f prime of 0 is 3. So once you replace x with all these constants of 0, some of the terms will drop out. And actually, it ends up being very nice. We end up getting c equals 3. So now we have our actual first derivative taken care of. So not plus c anymore, it's plus 3. Now, that's pretty good, but let's just check. They wanted us to find f of x, not the first derivative. But we can work backwards now, one more time. And we can say, okay, let's look for the antiderivative. And the antiderivative of f prime x should be f of x this time around. And now, let's see if we can incorporate that shortcut. These are all power functions, sums and difference of power functions. So f coming from f prime, you'll still have the 4. If you want to find the antiderivative of x cubed, it's x to the 4 over 4. We still have plus 3 times derivative, the antiderivative of x squared is x cubed over 3 minus 4 times antiderivative of x is x squared over 2, and antiderivative of a constant, you attach on an x. Last thing we need to understand is we need to account for that constant. So we can call it C. It's probably different than the other C. If you want to call it a different version, C1 versus C or C2, totally okay. If you're actually being precise, it's not going to be the same 3 that we just calculated. So I'll call it maybe C2. Before I try to approach the initial condition given, I want to see if I can simplify any further to make life easier. And it appears that the 4's divide out, the 3's divide out. 4 and 2 reduces. So I have a somewhat nicer function, and I still have plus C2. But now I'll take that initial condition that applies to my function. And that initial condition, I have to look back. That was f of 0 equals 0. I like it when they give us zeros. So what are we doing is we're plugging in zeros. And sometimes, I mean, you don't necessarily have to show that you're plugging in zeros. Usually I do this for the sake of if it ends up being any other number, we can't always do these mentally. But I'd like to just show you for purposes of formal notes. F of 0 is supposed to equal 0. So what ends up happening when we try to simplify everyone, we get a bunch of zeros except for C2, and that ends up being 0. So finally, we actually can now find who f of x is, who that actual c was, and it just happened to be that C2 was 0. So let's finish off the problem with our final answer. C won't always be 0, but it ends up being this case for this example. So now we found what the problem wanted. It wanted the f of x, the original function, given the second derivative. So we had to kind of go through two cycles of finding antiderivatives to actually find it. And so I hope that this gives you some experience with the sections. I do want to point out that we'll be using this shortcut a lot more, kind of what we were doing in example 5 and example 6. So if you're kind of catching on at this point, that's what we're looking for. The preliminary stuff was to get our brains thinking. So feel free, work through the homework problems and just let us know if you have any questions. I will see you next section.